Last winter, I got a call from a university research computing director. His team had just taken delivery of an 8 GPU H100 cluster, air-cooled, supermicro chassis, well-known OEM. The spec sheet looked excellent. The first 72-hour training run did not. Junction temperatures climbed to 83 degrees Celsius within 6 hours. The GPUs began throttling clock speeds. The system was running at roughly 70% of it. The training job that was supposed to complete in 4 days took 6. That 2-day difference represented approximately $40,000 in wasted researcher time and delayed grant deliverables. I have seen this story repeat itself at 4 institutions in the last 3 years. Different vendors, different GPU generations, same route. Air cooling cannot keep pace with sustained AI workloads at the power densities modern GPUs demand. That is not a criticism of any specific OEM. It is physics, and the gap between air and liquid is only widening as TDP climbs from 700 watts on the H100 to 1200 watts on the NVIDIA B200 Blackwell in liquid-cooled config. What happens when air-cooled H100s hit hour 6? The H100 SM5 has a 700-watt TDP. In an 8 GPU configuration, that is 5.6 kilowatts from the GPU array alone. A fully loaded training server draws between 10 and 14 kilowatts at the PDU. Air cooling moves that heat through high static pressure fans and rear exhaust airflow. Under burst workloads, this works. Under sustained 72-hour training runs at full tensor core utilization, the thermal management firmware reduces power draw by backing off clock speeds when junction temperature approaches 83 to 85 degrees. The GPU does not fail. It does not report an error. It simply delivers less than the performance you paid for silently for the duration of your workload. Your vendor's spec sheet says the server supports sustained AI workloads. Ask them what the junction temperature reads at hour 6 under full PyTorch training load. I will wait. According to Supermicro's October 2025 benchmark study, liquid-cooled GPUs maintained 46 to 54 degrees Celsius junction temperatures versus 55 to 71 degrees for air-cooled equivalents under identical configurations. Under sustained stress tests, the liquid-cooled configuration delivered 17% higher throughput. Power consumption dropped by 1 kilowatt per node, a 16% at 2,000 nodes. That is $2.25 million per year in electricity costs. At 5,000 nodes, $11.8 million. That OPEX reduction closes the CAPEX premium on liquid cooling before the 3-year mark for any sustained workload above 40% GPU utilization. Is liquid cooling more expensive than air cooling? The upfront cost of liquid cooling is 20 to 40% higher than air-cooled equivalents, but the Supermicro DLC2 direct liquid cooling platform demonstrates 40% power reduction and 20% TCO reduction over a 3-year deployment horizon, making liquid cooling the less expensive option when measured. The retrofit argument is where most organizations get burned. I have quoted retrofit projects for research institutions that bought air-cooled servers and discovered 18 months in that their cooling infrastructure could not sustain the workload growth they planned for. Retrofit cost for liquid cooling runs $2 to $3 million per megawatt of compute density. On a 500 kilowatt training cluster, that is a $1 to $1.5 million penalty for spec'ing the hardware wrong at what is the right hardware for AI training versus AI inference. This is the section that contains what I consider proprietary knowledge. Not because it is secret, but because almost no one in the GPU server market talks about it honestly. Vendors want to sell you the biggest configuration. That is not always the right configuration. AI training requires 16 GPU open-loop liquid-cooled 4U servers in multi-server clusters. A 16 GPU H200 server provides a 2,256 gigabyte VRAM pool per server. A 10 server cluster gives you 22,560 gigabytes of aggregate VRAM. That is the infrastructure required for frontier-scale fine-tuning, multimodal training, and mixture of experts. AI inference is a different problem entirely. You are not accumulating gradients. You are running forward passes on a frozen model and delivering results with low latency. An 8 GPU closed-loop, liquid-cooled 5U server handles this correctly. Self-contained CDU, no facility water connection required, installs in a standard company location rack. For engineer workstations and classroom environments, a 2 GPU closed-loop liquid-cooled work. The NVIDIA B200 Blackwell puts the liquid cooling conversation beyond debate. At 1200 watts TDP per GPU in liquid-cooled mode, air cooling means accepting a 200-watt TDP reduction per GPU, 16% less thermal headroom. You are paying for the full performance of the B200 and air cooling your way to 84%. The GB300 NVL72 takes this further. 72 Blackwell GPUs in a single rack scale unit, 70 times more AI flops than the previous generation. Liquid cooling is not an option at this configuration. It is a physical requirement. The power density exceeds what any air cooling system can. CoreWeave is the clearest data point in the market. 85% of their NVIDIA GB200 NVL72 clusters are liquid cooled. Only 15% of their AI compute fleet remains air-cooled. Microsoft is running pilot liquid cooling deployments targeting PU of 1.1 to 1.2, down from 1.6 to 1.8, projecting 50 to 75% cooling energy. The organizations I work with that chose air cooling 2 years ago now face one of 3 paths. Accept the performance ceiling and run throttled workloads. Retrofit at $2 to $3 million per megawatt, or replace the hardware entirely ahead of their planned refresh cycle. All 3 paths are more expensive than spec'ing liquid cooling at initial. I have deployed liquid-cooled GPU clusters at research universities, enterprise data centers, and organizations running production AI workloads at scale. The pattern is consistent. The organizations that spec liquid cooling correctly at purchase do not come back with performance problems. The ones that spec air cooling because it is the default OEM configuration. The question is not whether you can afford liquid cooling. It is whether you can afford to keep running air-cooled infrastructure that throttles at R6, degrades your hardware ahead of schedule, and burns 40 to 70% more cooling energy than the alternative. The infrastructure decisions you make today determine your AI capabilities for the next 3 to 5 years. Air cooling is technical debt. Let us build it right the first.